You're live? No, you're not live. Okay. Okay, welcome to Data Science Retreat Batch 30 Demo Day on a Friday. So you're going to see 5 projects that will help you understand better what is possible today with machine learning. And for those of you who may not know what Data Science Retreat is, we are a school that has been in operation for 8 years, and we have a very advanced curriculum, probably the most advanced curriculum in Europe. We cover topics that are not really industry yet, but will be at some point soon. So we don't train people for what's being asked on interviews today, but what will be asked in 2 years from now. We take people who already know what they're doing with an average of 5 years of experience. They all know how to program more or less. And we have 28 teachers that every teacher covers the one thing that know very well and leave. They are also industry practitioners, and this is the only way that I know to keep the standards high. Then the curriculum is advanced. You have multiple teachers. It's very intense. There are classes on weekends. It's really intense. And then the part that for me is it's defining Data Science Retreat the most is this thing that you're going to see right now, the portfolio projects. So here, what we ask our participants is to create a product or a tool that solves a real problem that somebody has. So this is not a tech demo of making something cute that you like. It has to solve a real problem. And that is a big ask. This is what entire companies, often with millions, the bank try to do and fail at dramatic rates, right? So this is what we ask people to do when they come here. And you can be the judge that they get there, and you will see here products that could be a company. And one thing that worries me a little is that people graduate and get job and they forget all the projects, and their projects are probably more interesting and more worthwhile to pursue than what the company that hires them is doing. So I'm still thinking about what to do with Data Science Retreat so that we create companies instead of creating people who join other companies. Okay, so this is Data Science Retreat for you, in case you didn't know. We value clear thinking, and we will do this more in the future. So there's a component of data science that is very human, which is making assumptions and testing them. So your judgment ability is really crucial to create value in any commercial domain or even any project that you do for yourself. Estimating a number, estimating the probability of something to happen, it's a skill. It's a skill that you can practice, you can get better at. So beyond the technical part of training models to predict things in the future, we want to help people practice the skill of making good judgments or good predictions, right? And what is a good judgment? So what is the probability of 25,000 people getting killed in the Russian-Ukrainian war? You may have a number in your head, right? Let's say by the end of 2022. Put the number on a paper, and after the end of 2022, check whether your estimation was correct. And this simple idea of checking your predictions and writing them with real numbers is the basis of clear thinking. And this is something that we don't practice enough, and you get better at it when you practice it. And this is a very important component of data science and of many other disciplines, really, that we want to start teaching here at DSR. So that's kind of a preview of something else that is not for this batch, but because you're here and you are curious about what we do, you're going to see really impressive projects that will help you understand what computer vision can do, what natural language processing can do. We keep adding new things to the curriculum. We have added graph neural networks, for example, on top of reinforcement learning and so on. You don't see projects on those topics because they come too late in the curriculum. So we're trying to fix that too. But what you're going to see here today, hopefully will help you understand what you can do, you as an individual, if you join us, and you as a company, if you hire one of our people. So there's a lack of, there's a bottleneck, which is imagination. So many companies are not doing things that are possible nowadays because they don't know that they're possible. And here you're going to see things that will help you understand what is possible. So we have 5 presentations. I'm going to introduce you to Madhuri, who is a computer scientist. Is going to show you what is possible with chatbots and visual question answering systems, where you can ask any question to a machine about an image and they will answer the question, which sounds really like general AI. So it's not really general AI, but it's very close to what you see in the movies. So, Madhuri.
Thanks, Jose. Hello and welcome to DSR Batch 30 presentation. I'm Madhuri and my mentors are Adam and Tristan. A big thanks to them. So today I'll be presenting my portfolio project, Sanjaya, a visual question answering bot with voice assistants. So this is the overview for my presentation. And there will be a demo at the end. So let's begin. So why Sanjaya? So for this, I will tell you a story from Indian epic Mahabharata. So Sanjaya, he was an advisor to a blind king, Dhritarashtra. He had gifted power of seeing the distant vision. So that means, suppose if you are a DSR and he can see what's happening in India, for example. So what Sanjaya used to do, he used to tell what's happening in the war place to the king. So the king, Dhritarashtra, he will be asking the question, who is the powerful person, who will be winning, and all those kind of things. So he was like a question answering machine for the Dhritarashtra. So Sanjaya was the VQA bot at that time, and my Sanjaya will be the VQA bot for this time. So that is the main reason for my motivation why I want to select Sanjaya. So basically, it's a fusion of NLP and computer vision with a talking power. Yeah. So what is a VQA system? A visual question answering. This field is quite a lot of this field is in research for quite a lot of years. So it's nothing. It's just a basic, you are passing an image and you are asking the question about that image. And this input is going to an AI system and an answer is generated. So it's simple question answering. So why Sanjaya? How my model will be different from the conventional VQA? So for this, I considered the limitations from the existing research things that happen in VQA, for example, like image captioning. So a person can caption image and all those things, but there are some limitations like image captioning. It's quite generic. For example, if you see in this on my right side, there are two people who are sitting in a wheelchair and one is holding a racket. But this information doesn't depict like what color t-shirt are they wearing, what is in the background, what they are holding. So it's like it's in the course, it's a course understanding of the image. It's not the fine understanding and it's not active. So the next game was VQA. VQA is, I'm talking about a conventional VQA. So conventional VQA, a user can actively ask questions, what is in the picture and what they are wearing and all such. You can see an example on the side, right side of my screen. Yeah, but mostly these kind of VQA system returns answer in single word. Yeah, so this falls short of rich linguistic capability of human. Human can do a lot better. So why VQA with full sentence answer? So this is the main motivation. Like currently we have VQA model, but with a short answer. But my VQA, that will generate a full sentence answer. So it's like more connected towards human. So human feels more connected. And with the previous VQA conventional system, it was like you feel not that connected because it's a single word answer. Here you get more interested, more motivated to go into the details of the things. So that's what. Yeah, so the application, what I can think of for this VQA model, like intelligent robots. Human can speak with these kind of robots and they can narrate, and the robot can inform about the surrounding images and they can do the work. For example, in house, there can be house robots, they can do the service in the home. The owner can say, please do this, please do that, something. So that can be a question answering thing. And it can also be in the case of product discovery. And yeah, and it can be very useful for visually impaired users. Already Facebook API has tagged the images. So with this information, we can develop quite a good VQA system. Yeah, and the next application I can think is like people who are not visually impaired, but they are situationally impaired. For example, people like data analysts, they have to analyze a large amount of data and they need to get information. So this kind of VQA system can be very helpful for them. They can just query and they can get the result from those visual data. I can think of like a surveillance system. In that, you will have a lot of terabytes of data of the video recordings. Then it's quite a big task. So the people can just ask the question about those detail, and you will get an answer very fast. Yeah, and even it's quite useful for medical professionals because nowadays we know there are like a lot of data available in visual way. So the doctor can confirm their finding by asking the question about the image, whether their finding is correct or not. So it can be one of the application I can think of. Apart from that, in educational industry also, it's quite useful. Teachers can use this and ask um, kids to study or something. I mean, there can be a lot of applications. That's what. Yeah, so this is my model architecture. So on the left side, you can see there is a laptop, that is the user. He will select an image and he will ask the question about that image. So for the question, whether the question is valid or not, my question validation module will have a check for that. So if the question is valid, then the valid question will be forwarded to WILT, a vision and language transformer. So after getting the valid question and the image, the WILT transformer will give an answer, girl. Who is under the umbrella? Girl. So that is the conventional VQA system. It provides answer in single word. So next, what I'm doing, I'll be forwarding this short answer string to a T5 small transformer. So the main purpose of T5 small transformer is to generate a sequence of character to make a short answer to a long answer. So the output of transformer will be like the girls is under the umbrella, but it may not be in a proper grammatically form. So for that, I introduced a T5 grammar module, and then this result will be passed to this grammar module, and then a grammatically corrected sentence will be visible to the user. So this side on the left side, you can see this is the chat part. On the right side, there is a audio bot, that is the audio integration with this functionality. So the functionality is almost same. You can see the flow. On the right side, there is a user. He's asking the question and about this image, and I used Facebook speech recognition that will convert speech to text, and this question will be passed to the question validation module, and as usual it will check for whether it's correct or not, and then if it's correct, it will be passed to the WILT transformer. And then a short answer will be generated, and the flow is the same as you see. Yeah, after the grammar module, it will be passed to the user in the form of audio. So for that, I'm using a speech synthesizer. So next, yeah, so I will talk about the data sets. Yeah, so I tried exploring quite a lot, but I was not able to find the data relevant for my problem. So what I did, I wrote all the data by myself. So it was quite tedious task. So it took around 5-6 days for me to do this. So you can see, for example, this kind of data I needed. So we have data like question and short answer, but I needed a data where I need a question, short answer, and the long answer. So this is the data format that the T5 small generator expects. Yeah, so now I'll go each and every module in detail. So as I said, my first module was question validation module that I did myself. So this module did a validation check on the question. So for this module also, I use the same data set that I created. Only thing I duplicated, like question, because it's checking whether the question is valid or not. So if question is valid, it is 1. Or if it is not valid, it is 0. So for that, I made all answers as invalid and I provided 0. So in this way, I duplicated my data set. So from 4,500, it became 9,000. So that was quite good size. So for that, I did a text vectorization, and then in a pipeline, I fed this data, and then I passed it to the logistic regression model. So logistic regression, I found quite a good result with that. It's almost 98%. So that was quite good. So the data, the question validity, even I have to check, it was really good. All because I had a very high quality data, maybe. Yeah. So after this question validation module, now we have a valid question. So this valid question is fed to the wilt transformer. So this transformer, I took it from Hugging Face. It's already pre-trained, so I didn't do anything much on this. Yeah, so I fed the image and I gave the question, and this module took care of everything, and it returned an answer in 1 word. Yeah. So next, once you got a short answer, the short answer is fed to the T5 small generator. For this, I did quite a lot of work. Yeah, whatever data I created, I pre-trained this completely on locally on my laptop. And then I fine-tuned on my downstream task. So my downstream task is to convert the short answer to the long answer. And this T5 is nothing but a sequence generator. Yeah. Yeah. Once the short answer has become long answer, then we need to check for whether it's grammatically correct or not, readable or not. So then I pre-used T5 grammar module from Hugging Face again. Yeah, and then this this grammar module has given me a quite good result, and you can see. And now I have a full sentence answer for a question that I asked about an image, and that also in a very good grammatically correct form. Yeah, and for speech interaction, text to speech and speech to text, as I said, I used WebKit speech recognition for speech to text and WebKit speech synthesizer for text to speech. These two libraries are provided from Python for by JavaScript for integration to Streamlit. Yeah, so this is the output. You can see, like, after wilt, I got an answer. I asked how many cars are there. It returned 0. So it's a 1-word answer. Next. This is T5, small, pre-trained, and fine-tuned, but not grammatically correct. Now the same question became, there is no cars. So now I fed this to the grammar module, and now you can see the result. It's proper. There are no cars. So this is grammatically correct, right? For deployment, I used spaces from Hugging Face. As front end, I used Streamlit. And the backend binaries, T5 and question validation pickle, I deployed at Hugging Face 2. So this is my model name, T5 small VQA FS. You all can find it online. Yeah. And now I will show the chat bot demo. And for AudioBot demo, because of technical glitch, I have recorded the clip. So once I finish chatbot demo, I will go ahead with audio clip. Yes, Jose, please, can you share the link? I have already slacked you. So this is my application at Hugging Faces. So I provided an option of chatbot and audiobot. So first I will demonstrate how this chatbot works. So you can see the results are quite convincing. Where is the cat sitting? The cat is sitting on the couch. What color is the couch? Yeah, the couch is brown. So if I give something that is not a question, let's see what happens. So it returns, I can understand only questions. Can you please ask a valid question? So for the audience and for the online audience, if you have any question, if you can see the image, you can ask anything. Do we have questions from audience? I think sleep is going. The cat is next to remote. How many remotes are there? Maybe that can be the next question. Oh, sorry. But still it gave the result. Yes. Yeah, so this is also a good feature. Okay, apart. You mean what kind of breed, right? Yeah, actually, this is one limitation that I will explain later. What kind of cat is this? This is Tabby. So it's telling some random name, Tabby. It's not saying the breed. I mean, we have to be very particular in asking the question. If I ask, how old is the cat? Let's see. Yeah, it's getting trained nicely, actually. The cat is 5 years old. Nice. Which question? I have a reason for that. Let's see. How old is the cat? No, it will not give now, because this is the limitation from Streamlit. Actually, it maintains the session state. So every question answer pair is a state. So now it sees it's the same state. So it's not returning. If it returns only, it's a new question. Then it thinks it's a new state. So that is the limitation from Streamlit. I can't do anything. Yeah. What? What cat has done? I don't know. This is some random question. The dog is sleeping with the dog. Some random answer. For random question, random answer. Yeah, sometimes it says some funny things. So yeah, basically I have to train it more, give it more data, because my data was quite high quality. So I got quite a good result. So yeah. Any other questions? Or shall I try with another image? Or what does think? What does the cat think? All right. The cat thinks warm. Is she hungry? She is not hungry. Which room is this? Let's see whether it identifies what kind of room is this or not. This is the living room. So it finds whether it's indoor or outdoor. It is indoor. Is there something, I will ask, which is not there? Something maybe is. Yeah, the why question, currently I'm not able to train for that, but yeah, it takes some random meaningful answers. Who question is okay. Who took? Who took the photo? Yeah, let's see what it says. Owner took the photograph. Correct. Yes. um, yes. So next I will demonstrate how I did with video, but I cannot do the live, so I have the clip with me. What is in the picture?
Man is in the picture.
What is he doing?
He is using a laptop.
What is in the background?
The fireplace is in the background.
Is the fire on?
The fire is on.
Is the man wearing glasses?
The man is wearing glasses.
Is the man young or old?
The man is old.
How old is the man?
The man is 70.
Which color is the laptop?
The laptop is silver in color.
Is there a chair?
There is a chair.
What is the chair made of?
The chair is made of wood.
Yeah. Okay, so you saw the demo. Now, next, moving forward. So, so you can see the result, what I demonstrated on the screen. Yeah, now about the results. For the question validation module, as I explained, I got already a 98% accuracy. So yeah, it's quite good. Next, for the T5 module. So for the T5 baseline module, you can see the figures. So my model performs quite better than the baseline model here in front. Yeah, so for conclusion, yeah, I presented a visual QA model with full sentence answers, and it can talk too. And I created a data set, quite a big one. Yeah, so current limitations are like, it doesn't understand the semantic meaning. I need to provide more data for more scenarios, more kind of questions to be covered. And the performance is little down because I had two T5 module. So what I could have done, I could have used single T5. In that I could have made the thing. So that then there will be only 3 models instead of 4 models. And yeah, because of the speech recognition WebKit, it runs better in Chrome browser. Yeah, and the large model like GPT-3, they are quite costly to train and deploy. So in future, I want to train more on the GPT-3, GPT-J kind of model to see how it performs, whether it performs better than my fine-tuned model or not. I want to have a check for that. And in future, I want to support multilinguality, like I can have a lot of languages, French, Spanish, and so on. Yeah, and better user interface so that it will be more good and feel. Yeah, so currently I use Wilt from Hugging Face, but in future I want to train myself on big image data set and to see and explore more about how it performs. Yeah, as you have seen, I haven't done the real-time audio integration, but this is in my plan. And also visual question answering for videos. You can connect me at this link. The project, the VQA project is deployed in Hugging Face, and the complete source code you can find at GitHub repository. Thank you for your attention.
All right, so time for questions, both in the audience here and the audience online. So I cannot really see the chat from online, but I mean, if you can tell me if anybody's asking questions, you let me know. So for anybody listening to this who may not be familiar with machine learning, you have seen how in a few weeks' time, somebody who was coming mostly fresh from another field, from computer science, who learned enough machine learning to build a tool that is pretty close to a non-technical person to magic. Like you can answer your questions by talking to the computer about any photo that you can upload. So Madhuri didn't demonstrate the part where you can upload pictures, but you can, right? So important that you make a mental note that this is possible with current technology off the shelf. So if you in your company have any kind of user interaction through chats or any kind of interaction where you could use voice to answer questions from a picture, then you should know that this is the state of the art. You can do this nowadays. So anybody has any questions? Madhuri is now running to the end of the room. Okay, Igor, you always have a question, right? Do you have a question? Okay, and come.
I'm here. You know, the question must be asked. Yeah, actually, thank you for the presentation. And this project is basically look like already idea for a startup, because yeah, I'm currently coming from the conference and there were startups which were doing less than you have done right now. Yeah. Could you please tell me, to us, all of us, what was the most challenging part in this project right now? Was it like working with the models, or was it deployment, or like finding the data, which data science it is does?
Yeah. Thanks for the question. Yeah. The most difficult part was the data and the audio integration. Deployment was quite easy. The most difficult I found was audio integration. That's what.
Thank you.
Okay, integration is the hardest part of this project. That's kind of interesting to know. All right. Do you need some time to connect everything? Okay. Right. So before we do the first and only switch of the night to another computer, I really wonder what will happen if you will take this presentation or any other presentation tonight, for that matter, to your boss. So what will he say? Will he say something like, "Yeah, I know this. I know that we can do this, and we are not doing it because reasons." So I really would like to know what are those reasons, because I have a really hard time understanding why we at Data Science Retreat, in a tiny room in an office in Berlin, do these projects every 3 months, multiple of them, but I don't see the same projects at companies that have millions, sometimes billions in the bank. So why is this not happening? This is a mystery to me, and I would love to know. So if you know, post it on the chat, or ping me, or LinkedIn, or whatever channel you like. Okay, so now I'm going to introduce you to Luise. She's presenting a project that has social impact, which is a big thing here at DSR. So we tell people the first day that they should aim for projects that help people, and it could be a project that people can buy, and then they demonstrate that it helps them because they're actually giving you money for it. This is a product, this is a commercial product, but often you don't need that. You only need to deliver value to a lot of people, and it's a value that is not necessarily monetary. In this case, the question is, how can you design cities so that they are sustainable? And can you use machine learning to solve this problem? And can you help the people who design the cities to do a better job and create cities that are more livable, right? And remember that machine learning, or AI as we call it for short, doesn't get tired of doing boring tasks. So imagine that counting trees from a satellite image could be done by hand, right? You could pay people for hours, maybe days or months, to count all the city's trees, right? That will be kind of boring and tedious and long, but it just happens that machines can recognize objects and also trees. So a machine learning tool can count all trees in your city. So Luis is going to show you how this works. So, Luis.
Hi everyone, I'm Luise Strate, and now I'm gonna show you or tell you something about my portfolio project here at DSR, Urban Eagle. So I'm not sure if you can now already see the slide deck. Yes, sure. Okay, we had a small transfer issue here, but now we are all set. So how did I actually start? When I first thought about what I could do as a project here, I thought, okay, urban sustainability, that is a topic I'm interested in. And how can I, with AI, empower urban sustainability? So, but when I asked myself that, I realized it's a pretty vague thing, actually. Urban sustainability, it's a buzzword, which comes up a lot and means a lot, and by that also maybe means not so much. So how can I empower actual urban sustainability with impact? Well, just a web application or equal is not going to do the job. It's not going to have the real impact. But what I really need is to actually find ones who who drive urban sustainability, and whom I can empower with information and transparency and everything they need to actually drive things. Now, who are advocates of urban sustainability? You might think. By that, I mean, first of all, it's city planners. People who actually change things, who plan where parks come, where trees come, how they're actually maintained, where construction sites are, where buildings can be constructed, etc. So these are the first people who have a real impact. Also, the citizens shape their surroundings, of course, in cities, in smaller towns as well. And of course, there's a lot of initiatives. There's NGOs, there's just small community initiatives who try to change with little projects. But where to start, where to go, and what actually changed, how to take track of things and make people actually reliant on what they have done. Well, and it's all about information. Where could I get this information from? Well, first thing that came to my mind was satellite images. Satellite images, as you can see here already, by just looking at this picture of Dresden, by the way, you see, okay, there's a lot of green, there's like a lot of grass spaces, maybe a little dry at some points. Also, you can see the water. And maybe if you actually know about this topic, you could say how the river itself might be doing, how the water quality is doing. You also see a lot of rooftops. Some would possibly be a good place for a solar panel, maybe. There's so many things you can see just from looking eagle eye view from top onto a city. That also actually AI can see if you teach it. So what does it actually need to get impact on urban sustainability and push projects which improve not only the environment, but also itself as a place to live? Well, I thought about 4 things which really are crucial here. First of all, of course, it must be relevant metrics and also understandable metrics, which all people can get a good grasp on and also understand what they actually mean. For example, count trees. For example, how many cars are there? For example, how well is the vegetation right now doing? Another thing to really get impact is it must reach a lot of people. So there must be a scalability, first of all, so we can use this tool amongst many different places on Earth. And also it must be accessible, so it shouldn't cost a lot, right? When now city planners, for example, try to get some information, often they have to finance really expensive research projects, and then also they might just have one timestamp of data, which then is really, really precise and accurate, but maybe also hard to understand. So the next thing would be really to make things comparable. One thing that needs to be comparing is how does actually a sustainability metric evolve over time? So what did change? What then we can also see if, for example, a drastic weather event happened, what changed after that? So there's a lot of things we can do when we just compare different analyses. of course, also comparing between regions, right? And get some real some real track on pushing cities and people who are in charge on performing on those measures. And the next thing, of course, it sounds dull, but I think it's really important that there's also some reliable reports afterwards with which you can share, which you can track, and which also make this whole thing more reliable. So those are the 4 factors I think are required to have real impact here and to really solve this issue. Now, let's come to what I actually did during the last few weeks for this project. I started with the intention of using satellite data because it is accessible everywhere, right? We have similar kinds of technology taking images around the world, so they're all used. They could all be used for the same analysis. Yet, unfortunately, the satellite pictures who are available for the whole world, and or at least for a huge coverage of it, and which are available for free, they don't have the right resolution. They have a 10 meter per pixel resolution, which you can already imagine is not enough to spot a single tree there. So I took another way, and I used Google Earth. This is pretty much, it's not exactly the same as when you open Google Maps, but it is actually the same data behind. So there is some satellite images, but also just images from planes, so aerial images. The major restriction with that is actually the size of image I could download. So everything I did is always with the pixel size of 2400 by 4800 pixel. And this comes to a resolution of 30 centimeters per pixel, which actually satellites today can do. But again, those images are then not free of charge. There is, or this exact thing, this exact topic is also the main limitation of this project, because it's always, for now, just small images we can download and analyze, and also sometimes for the way they are taken, they can get somehow skewed actually, so they are not in a really precise raster there. Also, we don't have geo coordinates, and we need to be a bit specific about which date to choose for weather reasons. Pretty simple. All right. Now I come to the 2 main features which I tried, since I think those 2 features represent the main metrics which are required to really make use of those images. The first type is object detection. In this case, I detected trees. The second type is semantic segmentation. So I took the image and pretty much divided the whole surface into different classes and different types, which you can see here on the right pretty drastically. All right, so let me first tell you about object positioning and finding the right localization of trees and also be able to count them. This was a 2-step approach. So first I actually identified the trees, and then I gave the position some fine tuning. So let me start with the identification. The first algorithm that already came to my mind and also was taught here is YOLO. So you only look once. This was the first thing that really seemed to fit, but not on the second look of it. So what I did is to adapt this logic a little bit, and the first step for that there was to actually separate the image into different tiles, which are all the same size. And those tiles then I would label as with tree or without. So this is also the same as with YOLO. logic. But if you just take one of those little grids there, you might just put one tree in there. So this actually works. They kind of cover about one tree, but you cannot really see the tree if you just see this one tile. It's just not possible. So if we can see it, also the algorithm won't be able to see it. So what I did is to expand each tile just for training and prediction, to actually to classify the tile within. And this is how it went. So I tested this, I self-trained a model, so there was no pre-training. Also, it wasn't a big convolutional network. It just had a few layers, but already performed pretty well on that. Saying that, also, as you can see in this F1 score, there's still more room to improve, but yet it actually already worked. You will see that later on. What comes out pretty much is labeled tiles. So the small, the small image on the left, black and white, is actually the tiles which came out as prediction here. So the white tiles are the trees. And on the right-hand side, you won't see that well, probably that's the original labels, but I'm just going to show you more of that. One issue here is the actual threshold. So the model is kind of sensitive to this threshold for different regions. It would work with one threshold, but it actually is a hyperparameter, which you can also later on use there. Okay, so this was actually to detect the trees. The second step then was to find position them. And this I did by regression of two variables, which represent pretty much the coordinates in pixel scale. So which pixel is the actual center of the tree? That was the question here. And this also I did with autokeras. So I used that for 30 trials, and it gave me out a ResNet pre-trained on ImageNet, which I then used. It wasn't trained on many trees, on many images actually, only 1,000 tiles. So it was a really small data set, but still it actually got the positioning better. It's not yet there, but also it's not crucial to the actual topic, which is detecting trees. And so this is definitely making the model better, but it's not crucial. All right, let me come to the second feature, which I tried, which just represents a whole nother type of feature in machine learning, semantic segmentation. So here I separated 4 different classes for the surface. First is what you see in red, the buildings, then the vegetation in green, water in blue, and other spaces are pretty much sealed spaces. So there's construction sites in there, there's streets in there, train tracks, though they have a lot of green around, and all things like that. So in terms of sustainability, maybe you could even speak about it of kind of lost space. All right. What I had was 2 images. One image as the input, the original one, and the output image, which I annotated, and which is the prediction of those 4 classes. What I did here is to use the RGB channels as encoding here, and I pretty much used the red channel for buildings, the blue channel for water, and the green channel for greens. And if no channel was activated, then it was black. So this is also how they can be shown then later on pretty easily. Though for the training, of course, all 4 classes were one-hot encoded. Then I used a one-by-one convolution, so a UNet based on the ResNet 50 trained on ImageNet, so over 100 layers. And what it pretty much does is it does the regular convolution, so it encodes the image, then there's a little bridge, and it goes back up pretty much, with also transferring some information from the encoding, and spreads it again to the same image size. So this is the decoding, and what comes out is hopefully something that looks something like the output here. So this is how I did. Actually, this is the categorical accuracy here. I only gave it 2 images which were annotated. So 2 images which are not really large. But as you can see in this picture already, for Dresden, it actually already is pretty detailed, and it's, to be really honest, it looks more accurate than what I annotated. So the model seems to be working already very well. So now that you can get a better grasp of it, there is a little demo here. So I deployed Urban Eagle already via Streamlit and GitHub. So if you wish, you can just join me right here and just go to this link as well and try also seeing some predictions. Is it sharing this one? All right, perfect. So what you see here is a picture of Berlin, first of all. So this is one input picture. And then there's the identification of trees right below. This is no live prediction. This is predictions I made before. Yet these are in future, probably you will also have those as live predictions and can upload your own images. And yeah, also is a more detailed view. So the ones with the pink rectangulars here, those are actually the trees which the model has found. Always on the left is the comparison without trees, so the original. And you see, okay, sometimes it might predict one tree too many. And sometimes also it goes to weird places, but all in all, actually it meets the spaces where trees are pretty well. This is the second feature here, so the semantic segmentation. Don't be irritated about the images having different sides. This is due to the tiling that you lose a little bit of space at the bottom and maybe also on the right. So the image of the segmentation might be smaller, but here you can clearly already see the pattern and where there's trees and where there's none. And of course, out of this, it's pretty easy also to get a share of the different surface types. But these cities are much like the presented, the training data. What if we go to Caracas, for example? So as you can see here, Caracas looks, or this district at least, looks different than a European city. It's got much more going on here. It's got much more structure. But if you look at the prediction, actually, they still work also with different lighting, etc. Same goes for semantic segmentation. So this is pretty detailed here, but it actually matches if you take a closer look, which you can, of course, always do later on, just going on the website. And another one may be interesting, Marrakesh. Because what you see here is that the houses are simply really different from above. And so let's see how the models do here. With the trees, you already see maybe not all the trees are captured here. So this is pretty clear to see here. But then again, maybe those trees are just too small because there's also some threshold for annotation. When it's a bush, it's too small. And when it becomes a tree, which you annotate. So that's not too far off from the annotation itself. And also for the semantic segmentation, it already works. See, it has been trained on Berlin and on Dresden images. So those two cities are pretty similar to looks from above, but this is way different. And still, it seems to work. All right. So let's come back to the presentation. And let me come back to the initial question which I had. How can AI empower the advocates of urban sustainability? I also gave you 4 criteria, which in my eyes are relevant to this. And let's go through them again and see where we are with this. Are we there yet? The first was coherent and relevant metrics, first of all. We've seen 2 types of metrics. There's a whole lot of things which we can still add, which are still pretty much close to what I tried before. So there are a couple of metrics already covered with that. Accessible and scalable. Well, it is, first of all, it's free online. If we can, or if I can get the API running to have images from all different locations just through the web app, that would be a huge step also to scalability. Comparable and objective. Well, it's an AI algorithm behind, so you can repeat it with the same model. You can do the exact same model, apply the exact same model on different times in on the same space, but different times to compare how things developed. You can also compare different areas with each other. So this is kind of given for this topic. And reports and UX. So here, no, we are not there yet, but yes, this is definitely possible with this tool. So I could tell you a lot about what next steps are in order, what next steps can be done. So there's a lot, but the most important message here is that this is a technical proof of concept for Urban Eagle, and to decide what features to develop next and how this can actually create real impact, real impact. I first have to ask the people who should make impact out of that. So the users of this product. So this is really the next step for me. So thank you for your listening. First of all, before you say anything, I want to thank my mentors. I want to thank my mentors, Antonio and Tristan, and of course also Jose, and all the teachers of Data Science Retreat. And if you want to, please just visit the website or also the repo on GitHub.
Okay, we have time for maybe one question, either online or here. And I have one question, perhaps, but this doesn't count. So, Luisa, I know that you talked to people already about this, right? So, to urban planners or people who are running this, right?
Not actually, not yet so far. So there was a lot of just really unofficial talks or just friends whom I talked about this with, but not yet concrete. But with this, I can actually show things and also tell people what I actually mean by this, because this is an abstract thing. Machine learning is really abstract. But I think with this proof of concept there and this web app, I can actually go to people and really ask them, hey, how could you use that?
Yeah, I think you're going to have an easy time, because this is something that you only need to find who is the politician that could place a big medal on his chest if he does this, right? And that's not difficult to find, right? And you have one in every city. So you just have to find them and put this in front of their faces and tell, like, see, this is what I mean.
It's hard to deny when you see those images, and when you see those images over time and confront people with it who are responsible for that, I'm sure they will have a hard time arguing against it, because it's pretty objective. You can see what comes out and you make it measurable.
Exactly. Okay, let me check. I mean, can you read the chat and see if there are any questions from online? No. Okay, cool. So thank you, Luis. Then we have Simon. So Simon, it's a physicist and handball player that is going to tell you how he mixed these two things together. So I don't want to spoil the fun. So here is Simon.
Yes, hello. Thank you. Thank you, Jose. So I was asked to share the screen. Share. Oh. Okay. It's physics, DSR physics presentation.
So we have optimized the workflow so that switching between presentations is as smooth as possible, but as you can see, we didn't succeed on this particular transition. I bet you something that for the next few ones, it's going to be very smooth.
Okay. So, hello. My name is Simon. I'm a mathematician. Yeah, I'm happy to present you my portfolio project. It's about teaching math and physics and use your self-made videos. Why is this? What's the issue? What is the problem? When I studied mathematics, I made two interesting and a bit shocking observations. First was when I told people I'm studying math, they said, so you will become a teacher. So keep this in mind. Second, I worked, had a side job as a private tutor. And the most frequent question while tutoring was, why do I need this? Where do I need this stuff? So these two things show a catastrophic mindset. Mathematics is just a tool for torturing. Yeah, you learn it to teach and to torture other students. Yeah, why is this so, and why is this an issue? Yeah, why is this an issue? We have a shortage of skilled workers. So this is widely known. So you need math and physics to study more sophisticated stuff like engineering and so on. but let's stick with the teachers. There's a shortage of teachers. There are way too few teachers with way too little time for teaching math. Yeah, and this may end or may lead to a vicious circle. Teachers have no time for teaching. Students are getting bored. They are bored by math, so they get even more bored. And that's the first vicious circle. Bored students are not really easy to teach, so I know this. Yeah, this leads to a lack of knowledge. This leads to a skills shortage, and we have too few teachers, and yeah, the circle closes. Yesterday in the news, you could read the reactions to an educational to the newest educational report. Teachers Association warn of a looming national emergency. So this is not just a problem of bored students. This is really an issue. This is a problem. So where do I think can we work on this problem? It's on the teachers, no time, and students are bored topic. There I tried to yeah, not just me. I tried to do more things that students are really interested in. So not just formulas, but give them exercises that may have to do with their real world experience. That's the moment when text assignments were invented. This is a solution, I don't know. They are still a bit boring. So 2 trains, A and B, and we all know this. So this is still not that interesting. What can we do? Yeah. In the second text assignment, we see, we talk about a parabola. So I really like the parabola. So it's the first, yeah, it's the first nonlinear function and the first mathematical object that you can where you can try and experience interesting things in math. So it's a non-trivial derivation and so on. So take this and have in mind we want to draw connections between the learning content and the world in which students live in. Though it's not by accident that I took sports here, because the laws of motion and parabola and sports, you can imagine there are these connections. Maybe we can use these connections to make math and physics more acceptable for students. So yeah, parabola. This is me throwing a handball. The first time since I think 20 years. Yeah, the idea is to have an easy tool that draws a connection between you doing some cool stuff, like throwing a handball, and you learning about parabolas. There are already some tools making this possible, but they are very time consuming and tedious. You have to draw these points by hand. Some already have features that automate some of these tedious tasks. I tried a few are expensive. Yeah, so why don't I write my own or develop my own tool for doing this? What do we need, or what do we want to have? We want to have an application that gives us an analysis of what is happening there, what is happening physically when I do something. So I use my smartphone. Kids and students have smartphones, and I make a small video clip of my performance, running, jumping, throwing a ball, send it to the program, and get the analysis and get the parabola, the values whatsoever. So how is it working? How do we go there? What do we need? First of all, we need object detection. Object detection and object tracking. They've made, yeah, how to say? There are mighty tools working very good in object detection and object tracking. Yeah, and I try to tell you a bit about how this works and how I use these techniques to build a tool that gives us a glance of the physics around us. First of all, object detection. You can use, or I used YOLO, which is a state of the art in object detection, can detect multiple objects at the same time. Detection of objects is just one part. The second part is object tracking. So a video consists of frames, of a list of frames, and if I have detection on each frame, I need to associate these detections to the objects I want to track. This is what we call object tracking. Object tracking uses a technique that's called Kalman filtering. And Kalman filtering, and that's the interesting thing, already uses these kind of information from previous frames, like motion. So how is the frame moving? And with the information, how is it moving? It makes a prediction where it will be in the next image, where one detection is probable to be detected in the next frame. If there is a detection and it's close enough to the predicted position, then it's very likely to be the object we want to track. If there are more than one, then we use the Kalman filtering with its probabilities to decide which is more probable to be the object we want to detect. I think this is a moment where I shall show you a video how it might work. And now I may need some help here, perhaps. So, wow, this mouse is really fast. Okay, thank you. So, okay, this is, can everyone see the video? Is it visible in the stream? Oh, well, I have here. Do you make a new share? Okay. So we see me throwing a ball, and you can imagine it's a bit hard to detect this ball, and that's one of the issues was not possible for me to solve in this time, to make this tiny ball visible. Let's okay. Okay. Is it working? Okay, wonderful. Okay, I'd like to show the next video now. So how do I go to the next video now? Okay. Okay, okay. Yeah, we see a next video. I recorded in slow motion, and let's jump to the video with the object tracking inside. Okay. Here you can see how Kalman filter works. This is very interesting to see. You see on the right side the sports ball and its ID 11, and sometimes it loses these ID, or it loses the detection. It loses the detection, but after a few frames, it detects it again, and because the movement is encoded in the Kalman filter, the association is kept. So even when it's occluded, or even if there's an occlusion. Okay. I think that should be yeah, enough. Okay. Okay, let's go on. What do we have? Yeah, we have now the object and its place in the image, and we have the tracking, so we know how it's moving. And the next step is to have a regression. To have a smooth function, and to see what's most probably going on there. What kind of motion is it? Is it oscillating? Is it a movement? Is it an accelerated movement? Yeah, we see the difficulties we saw. The object tracking is much dependent on the good object detection, which can be improved. Okay, what did I do? What is the workflow? I imagine students, or in this case me, had made a video clip of a sports performance. Then I used YOLO detection on each frame to make the detections of the object. The sort algorithm with a Kalman filter is the next step, and makes the object tracking. So we know we have the ID of one object, or of the objects and their movement. Next step is we have to decide which trajectory is interesting, which trajectory are we interested in. If we have decided for the sports ball, for example, I did a Fourier analysis and regression, and yeah, and then finally you can see a trajectory with a velocity and its vectors. So by now we have the step, we make a video, we put it in the physics AI analysis. We have to do some steps on our own, but not that much. Some steps we have to decide which object we want to track. And as a result, we get a regression curve. We can decide how exact the regression should be, how close to the measurement, or how close to the ideal parabola. Depending on that, we can then, do some exercises for the students. So this is the result from throwing a ball. Maybe we could last time watch a video, and this is the last slide. Yeah. This is the final output. Yeah. We see a flying ball. We have a velocity vector. We have a velocity vector. We can do our calculations on it. We can do exercises out of it. There's much math inside just the parabola. It is a function. You can see it as a function of time. You can see the x position as a function of time. You can see the y position as a function of x. So there are lots of things you can do with it, and you have the connection to the real world students are living in. So the problem of creating connection between math and physics and learning and students' activities, though, is solvable. We can do this. The required effort for teachers can be reduced drastically by using this framework. Yeah, and as a final result, the frequency of what do I need it for may decrease. So, thank you for your attention. Functional demo will be deployed soon.
Right. So if I understand this right, you can create exercises that are based on video instead of text, right? That's very important. But you could also personalize that to a ball thrown by one child who's learning, right? So
yes, yeah, exactly.
So there are two big things, two big improvements over the state of the art in teaching. One is going from text to video. Another one is stream personalization, right? It's my child throwing the ball, right? So how can he not care about that, right?
Yes, exactly. Yeah, an exercise for every student can be individually created by just throwing a ball.
Right. So there's a statistic that I didn't know, but 25% of the population of children have this dyslexia, which is they cannot read the text very well. It's very effortful for them to finish the text. And if the text is on top of that boring, like the train example that you use or the other parabola thing, they just cannot connect emotionally with the content. But at the same time, every child is interested in throwing a ball through a hoop or through a goal. And if you make the exercise to be about that, they for sure are going to care, right? So that's a big improvement.
Yeah, exactly. That's what it meant for. It's the attempt to draw the connection between math, physics, and the real world. Yeah.
Okay. So for our next presentation, we're slightly behind time, For our next presentation, we have Shah and Sebastian. They are going to go with yoga poses and voice feedback. So one common trend that you've seen is that people are building now interfaces that are voice-based, text-based, and image-based at the same time, right? This is how sophisticated the state of the art is for off-the-shelf models in machine learning. So you can build interfaces that understand and produce text and voice at the same time as they understand reality by looking at it. So the next two presentations are going to really consider that. And also one important thing is that you have more sensors now than ever before. So mobile phones have extremely good cameras that are already very good, but they keep improving with every generation. So taking a high quality video was not possible when I was learning, but now it's totally possible and commonplace. So we keep sending each other videos of high quality and big sizes, and it becomes completely normal. So for an app to take as input video instead of text, it's totally commonplace now in the 21st century, right? And you will see that this opens up the possibilities to build interfaces that allow you to do things in the physical world. So the gap that there used to be a time where you needed a mouse and a keyboard to interface with machines, right? Now this gap is much narrower. So now this gap is such that you can interact with machines just with your voice, with your face, with your expressions, with your body positions. You're going to see this in the next presentation. So in the next presentation, you're going to see how you can train people to improve their yoga poses just by using machine learning. So Shah and Sebastian.
Hi, everyone. Thanks for everyone here and online.
Hi, my name is Sebastian.
And I am Shah. Shahid, you can call me Shah, and we will be presenting our AI yoga trainer. Yeah, let's get ahead. So the pandemic has been a very big motivation for many people to start practicing yoga at home. Maybe we need to turn off the volume here, make it mute. Yes. Okay, then not. And many studios and or many yoga studios and fitness studios started offering online courses to people to be able to join from everywhere. I, for example, myself was joining yoga courses with big famous teachers from the US, from the UK, and all around the world. I'm just saying this being a yoga teacher. And the big difference between practicing yoga in a fitness or like at a yoga studio and online is the fact that online there's no one to correct your posture, no one to give you the right alignment on how to be in this or that asana. And this could result on the long run in having more or less bad posture, and also could cause some pain in the body. So we wanted to tackle this issue by, sorry. So the idea that we wanted to present here is to be able to keep a healthy practice in mind and how we can use AI in doing this. So our aim was to develop an app that is able to lead a yoga sequence, and at the same time correcting the person who is practicing through voice command. So for this project, we created a yoga sequence of 5 different asanas with transitions in between. And these asanas form the sequence that is led by voice, which we'll demonstrate at the very end. So talking about the technical aspects, we were able to identify key points in the body. And these key points were, I can show them here. where the main skeleton for the AI to measure the distance between these key points and identifying where this person is at the moment in their practice. Here's an example. It's an asana called Warrior One. This is on the left side, you see how it should be, and on the right side is how the AI was able to detect the alignment. This is a perfect 100% Warrior One asana, and so not a lot of people are able to do this, but this is how it should be. How does the app work? So the app is able to identify the asana through these main key points, as mentioned before, and then setting a score more or less if this pose is now in the correct or close to the correct asana through the voice commands. And these commands are connected to the breath. So the app is leading with an inhale and exhale as if there's a teacher in the room or in the class who is teaching this class or this sequence. Yeah, and the app is able to identify the current asana. So whichever asana you're doing, the app will be able to identify it. And yeah, once it's able to calculate the angles and the alignment of the lines. So how does this app work, calculation work, Sebastian?
Okay, I take over from here. So I will explain the technical details about this project here. Okay, so the pose detections for the movements are done using MoveNet and TensorFlow. So MoveNet is an ultra fast, as you can see here in this picture, for instance, and accurate model that detects 17 key points. So these are these body key points that Shah just showed. And here's the architecture of MoveNet. So MoveNet uses a feature extractor called MobileNet version 2, which is a lightweight convolutional neural network that was designed to work on smartphones. And it also comprises of 4 prediction heads that are attached to the feature extractor. And that makes the key point detection very accurate and also very fast. So we train a pose classification model using these pose detection from MoveNet and TensorFlow. So in brief, so here's a workflow that mainly consists of 2 steps. So first is we obtain the key points from training data that we scraped from Google Images. In total, we obtained around 400 images for each of these asanas. And then, along with the ground truth pose labels, we stored them as CSV file as an input to make pose classification and train a pose classification model that takes the key point coordinates as input and outputs then the predicted labels. So here are the results of this pose classification. So in total, we had around 2,000 images. 90% of them we have chosen for training and validation. And then on the right here, you can see a confusion matrix that shows the model performance. So it's about 10% of the images that were used as test images. And you can see that it's actually performing quite well. So next, what we implemented is a pose correction algorithm. So in order to make pose correction suggestions, we determine key points from reference poses, so basically perfect poses, and then calculate the angles for each of the joints. And then we also store them in a CSV file that we can then use in the algorithm for making the comparisons. So next we then compare the key points of the reference poses with key points that are determined from the camera frames. And then we measure some values like the mean square error of the angles, the cosine similarity, or just the angular differences between the reference pose and the pose that was captured by the frame. So here, oh, that was too fast. Yeah. So using key point calculations to make a specific pose correction suggestions. So here's an example. So on the left, you can see for the perfect pose, you can see the angle is 90 degrees on the right leg, and instead the pose that was captured by the frame only has a 110 degrees. So basically the correction suggestion that is made by the voice commands then would say bend the front knee. And you can also see that one of the arms is not high enough. So then another voice command would also say that the arm should be lifted a bit higher. So the next, what we implemented is this yoga sequence. So here, each sequence step starts with a key pose identified through pose classification and mean square error score. And for each of these key poses, correction suggestions are then made. And once the score is below a certain threshold, then the sequence continues. And this continues until the entire sequence is completed. So this, of course, is just a proof of principle. So in general, this can be trained on many different asanas, and this we are also aiming for the future. And then we would like to develop this further into a mobile app that can run on mobile phones. So next, we will demonstrate how this is actually working. And Shah will perform the sequence. Because you muted it, right?
So the app is going to give feedback through voice, and the setup should be such that you will hear the app talking. This is one of the demo effect things where it works 5 minutes before presentation and then it stops working when you're live. You need to be the host. Yeah, but this is not the way. So now we need to get the audio from, there are 3 computers on the table right now. We need to get an audio from the 3rd computer. Yeah, it works. Okay, so live effect is overcome somehow.
That's correct. Inhale, bring the arms over the head, palms touching. Exhale, fold down, Uttanasana. Inhale, come up to the fingertips, straighten the back. Exhale, step the right foot to the back, left foot to the right, downward facing dog. Inhale, come forward into plank. Exhale, Chaturanga. Inhale, upward facing dog. Exhale, downward facing dog. Inhale, forward into plank. Exhale, knees, chest, and chin. Inhale, snake to the front, little cobra. Exhale, tuck the toes, seat to the heels, downward facing dog. Inhale, step the right foot in between the hands, back heel on the mat, warrior one. That's correct. Inhale, exhale one. Inhale, exhale two. Inhale, exhale three. Inhale, exhale four. Inhale, exhale five. One more inhale. Exhale, open the warrior two. Keep the front knee on top of the ankle and extend the arms to both sides of the room. Look towards the fingertips of the hand that's in front. That's correct. Inhale, exhale one. Inhale, exhale two. Inhale, exhale three. Inhale, exhale four. Inhale, exhale five. Inhale, extend the front leg. Exhale, lean forward, dive down, Trikonasana. That's correct. Inhale, exhale one. Inhale, exhale two. Inhale, exhale three. Inhale, exhale four. Inhale, exhale five. Inhale, press with the feet, come all the way up. Exhale, bend the front knee, warrior two. Inhale, dance back, dancing warrior. Exhale, hands on the mat, downward facing dog. Inhale, come forward into plank. Exhale, Chaturanga. Inhale, upward facing dog. Exhale, downward facing dog. Inhale, forward into plank. Exhale, knees, chest, and chin. Inhale, snake to the front, little cobra. Exhale, tuck the toes, seat to the heels, downward facing dog. Inhale, walk with baby steps to the front of the mat. Exhale, fall down, Uttanasana. Inhale, come all the way up, arms over the head, palms touching, Urdhva Hastasana. Exhale, arms alongside the body, Tadasana. That's correct. Inhale. Exhale, one. Inhale. Exhale, two.
Shai is, among other things, he's a
Inhale.
yoga teacher, a famous one in Berlin too. So.
Exhale, three. Inhale. Exhale, four. I never stop. So yeah.
Yeah, unfortunately, the lighting conditions were not optimal, so not always all key points were detected. But at least it showed.
Right. So questions.
Where do we see the questions? Does someone have a question? You have questions, Igor?
Okay. Hi. Thank you for the presentation. This is a really amazing app, and yeah, just running just perfectly. Are you going to deploy it somewhere and make it publicly available, and when?
Yeah, I think this is our project, right? We definitely want to bring this to life, and we want to develop it further and make it work with different asanas and expand it, and hopefully we will be able to release it and make it available for people. Yes. Thank you, everyone.
All right. So, oops, echo. As you've seen, we made some iterations over the yoga idea, and every generation beats the previous one. As you can see, this one is really a fully formed app that actually even gives you feedback, right? So we are not live right now. We are? Okay. Right. So this is a good example of how you can use sensors like a camera and give feedback through speakers, which everybody has in their pocket right now, right? So everybody has experienced probably during COVID how it is to take lessons on anything physical like dancing, yoga, gym stuff at home. And as you can see, this type of apps could be really useful in those situations where you don't have a teacher that can give you feedback directly, right? And even if you can go to a gym or to a yoga studio, it's expensive to pay for a private lesson, right? And the same way that you've seen this working for yoga, you could imagine it working for dancing or for CrossFit or for any other activity that you do, right? Okay, so that takes us to the last presentation of the day. So you may not have noticed, but computers are, like the computers are driving our cars, for example, are deaf. So what will happen if you will give ears to a self-driving car or to a computer that is making life or death decisions for you? Can computers point at things in space and indicate where the sound is coming from? Because you are so used to doing that that you don't realize that this is a complex skill. And not that many computers do this today, or basically none of them, precisely because it's complex. So here are Chris and David, who are going to show you how they solve this problem. It's a super complex problem to solve, both in hardware and software. So you're going to see a lot of crazy setup here, and also some humor. So
thank you very much, Jose. Thank you everyone in the audience, and especially logging in from online, for making it to the final inning. Quick introduction. My name is David Alganavi, and this is my colleague.
Hi there for everybody.
And a special thank you to Dr. Tristan Behrens and Adam Green, who mentored us through this project. Now, this is like a quick overview of the agenda for this presentation. And we start off with an introduction. So hearing evolved as through evolution as one of the senses in most animals. And it was one of the senses that was needed for survival. Most animals can hear, and they can either find out where the prey is, or if they are the prey, where the predator is. However, when introducing the problem to a machine, it often is a bit confused on how to approach this problem, where the sound is coming from. And this was something that was introduced, which has also been a motivation for us, in a 2022 paper by Andrew Fransel and Josh McDermott from MIT. The purpose of their paper was to emulate human hearing and to learn more about how humans hear, how are they adapted to the environment, and for that they developed several deep neural network models. They trained on artificially simulated and real-world environments. And a little bit of background for the title of this project is Master's Voice. This is the old-timey logo of a record store in the UK, HMV, but under its former name is Master's Voice. And the anecdote behind it is when the master is away, he would play a record and the dog would come to the gramophone and listen to his master's voice. And we thought, what if we could introduce a robot or a machine to do the same thing? Question is, how does audio localization in humans work? And the paper by Josh McDermott and Andrew Fransel determined to find this out. The way humans localize sound is mainly in the difference in time of the sound waves reach the right and left ear. Now that difference can be infinitesimally small, but it is that tiny little difference where that parts of the midbrain are specialized to compare. And this is known as the precedence effect, particularly also the distance between the different sounds. So for example, if you have two sound sources and the timing between the sounds is minutely small, then the human brain will determine that it's just a single sound source rather than two. Whereas if they are further spaced apart, it will determine it as two. Now, the paper model developed several convolutional neural networks. Now, convolutional neural networks, they're a class of artificial neural networks that use convolutional kernels. Now, what you need to think of this is, imagine a picture, and then you have a little frame that slides across the picture, step by step, determining every single important feature in order to determine the difference as part of the model's training. What they have used is a Cauchy-logogram, and that was a type of spectrogram that was specifically determined by MIT, by Josh McDermott. And ultimately, it was an adaptation of a MATLAB code and especially designed for this paper, for the purposes of this study. Our motivation was, could you standardize it? The Cauchy-logogram is highly specialized, requires a bit of know-how to apply, whereas MEL spectrograms are bog standard out of the package, out of the box of package solutions, which you can install. And what you essentially have is an image generated of the sound waves. And in the words of our mentor, Dr. Tristan Behrens, convolution doesn't care. And ultimately, our motivation was, could we simplify the machine learning, the supervised machine learning task by streamlining the data pipeline, data transformation, and prediction? And to the applications, I pass it on to Krzysztof.
Right, so we were thinking about something very practical to try and solve. We were thinking how this paper that inspired us would or could be applied in practice. And our first connections were to the music industry, when there is very many specialized problems on microphone placements in studio, recording environments. So fast and lightweight solution to placing properly microphones would be a great addition. We can think of of entertainment industry, the whole gaming applications, when we can imagine, for example, horror games which scare the gamer from a specific direction. If we think about VR, those sound effects would be played from the environment, and then we would need a specified equipment on the VR set that would actually know the direction of sound. This could be either determined with what we are planning to accomplish or some other software applications. But the most important one, and I definitely love the picture that I found of a car with ears, is that as Jose also mentioned, autonomous driving for now is deaf. And I did a little bit of research, confirmed that. And our idea, for example, was that a car that doesn't see an ambulance coming from afar would hear it from afar and at least not perceive it properly, but pass a warning to the system of driving that would go into a more safer mode. A different approaches that we thought of were search and rescue. So where a rescue dog and a rescue professional are not able to find a person, maybe an algorithm that would show a general direction of a very silent sound would be great. Well, on the other side of the scale with the military, when you shoot and you don't know where the shot came from, that could also be somewhat an application, although exactly the opposite of rescuing somebody. So let's talk about software and hardware that we wanted that we had to develop to do this. And one short comment from my colleague.
Yeah, so our first prototype was Ludwig, which you can see here. The reason for the name Ludwig is because of Beethoven, how he was deaf, and we tried to teach our robot to hear. Then Ludwig used specialized microphones for this, and we wanted to see whether this would also work with different hardware. So ultimately, we wanted to try out different hardware, and we kind of thought Ludwig was a bit lonely. So we constructed Ludmilla, and thus explaining the origins of the Book of Genesis. And a bit more to the details. And over to Krzysztof.
Of course, well, the man was first somehow in this case. So we planned the whole setup with a proper USB audio interface that allowed us to use two specialized measurement microphones that are used in stereo calibration, SonarWorks and Neumann MA1. Sound freaks and audiophiles will know what I'm talking about, but it's maybe too specific. For Ludmilla, we just bought two very cheap omnidirectional conference microphones to also compare. Now for the software, except programming a lot in Python, we had to use some very specific software to prepare our data in the beginning. Well, we used Ableton 11, so a professional suite for audio production, recording, and development. We found a very good quality plugin that allowed us to artificially augment our samples to modify a dataset, MNIST spoken digits dataset, to make it stereo pan, so being basically heard by the listener from different directions and different elevations. So, but we thought that this was not going to be enough. Artificial data will definitely not be enough. And let's hear about the whole data production facility, which was mostly David.
Thank you very much. So yes, first we started off with artificial data set and hoped to be able to train the model on this. And for that, as mentioned, we used the Dear Reality plugin, which we could use to direct elevation and azimuth, in other words, to determine direction and level from which the sound emanated from. And for that, as you can see in the central tiles, we have up, level, down, with Ludwig or Ludmilla in the middle. And something you're going to hear very often for the rest of this presentation, directions label sectors. So we divided the room into 8 sectors, starting from 0, going all the way to 7. And for our first try, we use spoken MNIST data set. So now the spoken MNIST is, you just have to picture someone shouting a bunch of numbers for about 20 minutes. It's a pretty standard data set which you can download from TensorFlow. These were sampled at 44.1 kilohertz. And what's incredibly important is that the output has to be 16-bit WAV files. Another hard lesson learned. And for our data collection, we essentially, we had the room with Ludwig in the middle, and we essentially went around dividing the room into each sector with a Bluetooth speaker, which I think we have here. Yes. And as you can see, we had a rudimentary contraption where we tied it to a stick. So, and yeah, for this process, you could say I had assistance of 2 poles. Get it, because he's Polish, but anyway. So the original data collection was spoken MNIST, and we played this around the room for each sector 20 minutes. But it turned out after we tried out our first iterations of running the model that this was a bit too simplistic for a real life scenario. So what we've done then is we've done 2-hour recordings of a random composition of complex spoken word from the library speech TensorFlow dataset, 2 hours for each sector, and 1 hour for each elevation, mainly because we wanted to ensure essentially our benchmark model was that it determined the right sector, with elevation being secondary, as essentially direction was deemed to be the more important one. And then we wanted to see how it would compare to unexpected information. So what we've done then is we've recorded several in all of the sectors, essentially reading out to Ludwig a list of English kings and queens. And now he is very familiar with the English monarchy. These were then developed into, we developed a Python routine that cut data into 1 to 2 second WAV files, which were then transformed into a spectrogram and serialized using Pickle. Now, this is very important because you don't want to have God knows how many thousand files being fed into the model one at once, because it takes up too much memory. It's much faster and more efficient to have it serialized using Pickle, which is another Python package. And processing took about 15 to 30 minutes per sector, just depending on duration, just to give you an idea how much processing there was involved. So a lot of time. Now, data collection, to give you also a flavor for the extent of how many samples we've had. So we've had artificial MNIST, which was the spoken digits. We had live MNIST, and we had live complex. For each category, 72,000. So that's a total of 216,000 samples. And as you can see, the technical term, that's a big ass data set. And remember, it's not cursing if I'm talking about donkeys. And what is also important for the model is to ensure that you have a uniform number of samples, because ultimately, you want to avoid data imbalance where the results might be skewed in favor of one sector or one elevation. And most importantly, is also the way you feed that data into the model. Because if you feed it,
always shuffle your training data.
The more you know. The reason for this is if you feed your model in a sequence 0, 1, 2, 3, 4, 5, 6, 7, it's not going to predict any of the sectors. It's just going to predict the next thing is going to be 8. So you want to keep the model on its toes and feed it different data so it doesn't make the error of thinking that it's predicting something that it doesn't exist. And so for the model, we had actually a number of models at our disposal from different papers. We focused on 10 different models from the McDermott and Frenzel paper. And we've ran the training with them. And we picked the one which had the best performance, which was model 7. So we've had a pretty good validation accuracy and a training accuracy, validation accuracy being the orange line, training accuracy being the blue line. And this is ultimately the result we aim for, with the validation accuracy being somewhat better than training accuracy. So we have a good indication that the model is not overfitting. And this is just a quick overview of how the model looks like. So you have 3 and 4 blocks, which are broken down. The 4 blocks include a max pooling layer, which basically reduces then is a form of downsampling, which reduces some of the parameters. And ultimately what you then have is a sequence of 3, 4, 3, blah, 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 to a fully connected layer. And you have a softmax activation, which gives you then the probabilities for elevation and sector. And now to further details regarding the predictive modeling part to my colleague.
Thank you. So an interesting illustration of what we did, and what we did quite different than what we learned in our classes here, because usually we treated mono samples, so one channel. Now, key difference is that we have 2 channels, left and right, for stereo, as ears on a person, or Ludwig, apparently. And then, as you can see, sector 0, which on the map is facing you hearing it from the front, and now, as we can see, a data from sector 2. Now, it is quite illustrative to see that the left channel is much weaker, because the sound source is now in sector 2. So the listener hears different frequencies, less frequencies, or lower intensity, lower volume in the left channel than the right. This introduced a few problems that we had to solve with the placement of the microphones, because, as you can imagine, if this effect is exactly the same on the other side, then it's very hard to distinguish front from the back. But proper alignment at 90-degree angle solved this issue for us. And now this is about results. So all the models with the David speaking English monarchs to poor Ludwig, and our test predictions, right? So our expectation, as we assume and how we cut them, the samples per sector are the same number, we would expect a uniform distribution, right? Let's say 100 samples per sector, feed it into prediction. We want to get 100 predictions of sector 0, 100 predictions of sector 1, etc. Now, the best we got was 96% prediction with test set, which is already quite satisfying and showed on the slide. It did misrepresent a few, but in general, he did not. For example, he had a problem with sector 1 on slightly to the right. So most trouble was in those in-between sectors, left, right, front, and back, because of the microphone alignment was quite well predicted. And this, as we follow the visualization scheme, is actually David talking to Ludwig and how Ludwig perceives him, and our percentage values. Now, in our sector map, as you can see, it's a sample from sector 5, so we're very happy with this random sample chosen for presentation, that the model was very sure, 99%, 99.9% sure that it was sector 5. And for elevation, he was very sure, so 80% that it was a leveled sample, which it was. But he assumed in 20% that it was a lower level, so the source would be closer to the floor. But we are very happy with those statistics. Now, to let's say entertain you and our audience a little bit, we have used significant amount of time to develop this as a live feature. Now, because you would think that, you know, you say something to Ludwig, you record it, then you feed it, then you wait a few minutes to get a prediction, visualize it in the next few minutes. No, we actually developed a live app that incorporates multi-threaded processing, listens to both input microphones live, then waits for a sample to be finished with the resolution of about 1 to 1.5 seconds. This depends on the hardware actually. Then it live feeds it to model and gets prediction for direction and elevation and shows it on a graph. So in the meantime, David will comment on some future improvements and I will prepare the live demonstration.
Thank you very much. So some of the issues we had when faced down the road were partly in terms of like parallelization of different tasks so that they would run at the same time. This was quite tricky, in particular with tethering and applying it within Python. So because normally it's used to running sequentially. Other thing, microphone compatibility with different software, audio plugins, software plugins, compatibility between Python packages and the hardware. So for example, for the Mac M1 with TensorFlow, there had to be a lot of workarounds to get it to work. And one of the things which we want to see in another iteration is see how the model performs with PyTorch. Other instances where, and I think my colleague would like to introduce Ludmila. Yeah. That's fine. And now we move on to the, hopefully, live demonstration.
Well, you don't then stop talking. There will be problem with, there will be problem with lag or synchronicity here, although Ludwig would be expected to notice sounds in front of him, and Ludmila, well, as well. We can see and wait for a few seconds if there is any agreement between them, as I mean, suggesting a married couple struggles to decide the direction and elevation. Although the model was not exactly performing perfectly on live conditions, I definitely saw a proper sample prediction at some point. It may be hard to catch, but the most important thing is for us that we made 4 microphones worked in synergy, synchronously, multi-threaded applications, and proper and very appropriate predictions done by our models, which makes us very happy.
As happy as parents could be. Bear with us for a short moment. We'll just quickly run through this whole thing again. Okie dokie. So that was a live demo. Yeah, so just a couple more comments in terms of like sensitivity of microphones. So this environment was, I'm not sure if you can hear from your side, but it produces a lot of echo, which could interfere with the sensitivity of the recordings and cause a lot of interference. But ultimately, we also had an attempt at transfer learning by applying YAMNet and CREP. Unfortunately, this instance of Frankenstein's monster did not work, but it leaves open scope, further scope for implementation and seeing whether there are any other models out there which we can use and see if we can attain a better result. And yeah, thank you very much for your attention. Apes together, strong.
Okay. So this is actually the logo for the team. As you see, they communicate in memes and they communicate in funny ways anyway.
I mean, as a comment, Jose said on multiple occasions for us to drop the internal artificial language that we developed for the sectors, for the data sets, because if you heard us from aside, you would not understand anything if you weren't corrected. It was like, so David, how is the level 45 up complex sector 2 data? Exactly.
Right. Okay, questions from the audience, questions from the room. So we have Question Man coming back.
Thank you, guys. Really nice project. The question, general question, actually, I was going around and already discussing your project, and different guys asked me quite the same question, which I would like to address to you right now. And so you have already answered it a little, but please repeat the answer once again. Obviously, this problem with audio source detection should be already solved with classical approaches. Why haven't you used this one and you moved to the artificial neural networks? Please explain it like one more time to be clear that no one will ask you again.
So I believe we discussed this on a few occasions. Well, we wanted to do it faster with less sophisticated equipment and as lightweight as possible, although those algorithms are based on very sophisticated, very precise measurement devices that not everybody could get their hands on, or their development might be difficult, or their handling too complicated.
And just be sure that I understood your question properly. So why also we opted for artificial neural networks as opposed to a conventional classification task? So ultimately, sound is very complex, particularly when transformed into an image. You have a lot of features, and just like in a feature, this is where convolutional neural networks absolutely, because there are a number of different features, as we've seen in the spectrogram, in terms of where the location of the sound source, like how it's portrayed on the image, the tone, the strength, frequency, strength of the signal. And these are all things that are perfectly designed for convolutional neural networks, because they can factor in all these different variables, which I would say, as an educated guess, classical models would have a bit more of a tough time with.
So you trained your model mostly on human voice, right? Do you have any indications as though this is transferable also to other kinds of sounds, or is it very specific to voices, human voices?
Well, we did not many samples, although whistling worked quite well. That was for sure. We also screamed at Ludwig when he misbehaved, and those were classified also quite decently, although a very crucial characteristic for the predictions is the loudness, unfortunately, and this is very dependent on the setup. So, for example, we cannot exactly control the input volume for conference microphones. We had a very good control for the specialized microphones, and this was a very big difference. It basically dictated the effective range of the device. And for Ludmila is about 1 meter. For Ludwig, it's this classroom, which is about 3 by 3 for our measurements.
And ultimately, the model is very much not just data dependent, but also labeling dependent. So if you train the model to look out for different features, so rather than maybe spoken MNIST or spoken word, but particular other aspects, like, for example, vehicle sounds, sirens, then it would be able to pick those up with sufficient training and data as well.
One more question from Igor, question mark.
No, actually, this is question not from me, but from my boss. He's an audio expert.
Oh, sure. No, a microphone for 25,000 euros. Yes, I love those, but I can't afford them.
So, okay, just I just said, why haven't you used the special KU100 microphone?
Money.
Money, exactly. If you are suggesting you will provide it for us to do research for you, I'm in. We could afford 15 euro microphones, and I by accident had the nice measurement ones, which I acquired by while calibrating my own home stereo system long time ago, which was just a coincidence.
And just for your boss, like, with sufficient funding, we'd be able to find him also the burning bush. So
Exactly. I would measure the sound of the light bouncing off the moon if you gave me enough money. Anything, man. Any other questions?
Right. So people are saying good things on the chat online, but no questions. So I think this is a good moment to call this a day. And thank you for everybody who made it all the way through the end. If you like what you've seen, tell people to come and find us. We are a tiny little room in a city in Europe. We're doing this thing with, as you see, not that many resources. Just find us somebody with millions or maybe billions, and we will do better things, not only with better microphones, but we will make these things real products that will make people's lives better. So I want to do something bigger with this, and I want people to graduate here with companies and not jobs. But I'm very happy the way it's working right now because people do get jobs. But if you want to do DSR, apply. If you don't know if you can actually go through DSR, still apply because you may be underestimating yourself. You're going to interview with me. If you know somebody who could do DSR, freaking tell them, because they have a super easy way now. The unemployment office pays for this. It used to cost 12.5K. Now mostly everybody gets it paid by the unemployment office, which is amazing. So very good idea for German government to do this. It shortens the time that they have to pay out money to people who are unemployed because they get jobs, right? So great idea. And in any way, help us getting the word out. So the only thing that we do for marketing really is word of mouth. So the way people find us, everybody who's in the room found us through word of mouth, pretty much, because we don't do very well online. We don't do Facebook ads. We don't do LinkedIn. We don't do any ads because every time we tried, we failed. So the only way for people to come here and do things like this is if you tell them. So help us getting more people to do things like this.